Hi, Bobby.
Hi, Chandaka.
So, if you remember,
TMR.
yes,
Okay.
we did AMR and then
GMR,
GMR,
TMR.
TMR.
Is there anything more?
I think let's 3 is enough. But
Okay.
So we looked at some applications of GMR,
Yeah.
the magnetic hard disk.
Correct. Oh, that was amazing.
Yeah, that was very nice. And then we also discussed about biomedical applications of these GMR sensors, making the small biochip.
Yeah.
So
Magnetic beads.
Yeah. Yes. So I think the last thing we talked about was we have a bead. If we magnetize it a certain way, let me change the color. Right?
Yeah.
Let's say you have an external magnet here, right?
Yeah.
And you magnetize it, then this will produce a stray field. Okay. And then if you have a GMR sensor below this magnet, you will be able to detect these stray fields.
Okay.
Based on the number of beads that you have on top of the sensor, we can measure the concentration. Okay. Of course, these beads are connected to some biomolecules or cells or so on. But the disadvantage we talked about was because this field is in opposite directions, this stray field is very, very small.
Small in value.
Yes. And also this external magnet could be quite large.
Yes.
So it kind of defeats the purpose of having, having a small chip. So ideally, what you want to do is integrate your magnetic sensor and your beads along with this external field all in one chip somehow, right? And hopefully also increase this stray field produced by the magnetic bead. So one method of doing that is, so you take the magnet out. Now on the little chip that you have your GMR sensor here, okay? And then if you have a conductor very close,
Just
a conducting wire, let's say a strip of copper or aluminum or gold, right? And now all these are done at the micrometer level, right? So you see the difference between if your magnetic GMR sensor is 3 micrometers, the conductor is also 3 micrometers, and they are 3 micrometers apart. Now, if you give this conductor a current going in, okay, then you get magnetic fields like this.
Okay, so there is some current passing through this conductor.
Yes.
That produces its field. Okay.
A localized field. Okay. And then it will create a dipole moment in the magnetic bead, which in turn will create the stray field.
Oh.
Now, in this case, depending on how close your bead and your conductor is, how close your GMR and your conductor is, it will produce a stray field. Hopefully, that the majority of it will be on top of the magnetic sensor.
Okay.
Right? The other...
So the permanent magnet is not there now?
No. So everything's on chip.
So it's kind of an electromagnet.
It's kind of, yes, it is an electromagnet,
yeah,
right? Yeah, it is an electromagnet.
There is no core, there is no magnetic core,
no,
just a conductor.
Yes, correct.
Okay, got it.
But then a better way to do this is to have, now this could be TMR or GMR. So this could easily be switched, right? TMR, GMR basically measures the magnetic field planar to the surface. Now you could have your GMR sensor here, okay? And then you could have some kind of a passivation layer like silicon nitride. So this is your substrate, could be silicon, okay? Silicon nitride that covers the GMR sensor. On top of that, you have your conducting wire.
Okay.
And then that again is covered by some polymer so that this bead will not touch the conducting wire directly. Okay. Now, when you produce again, if the current is going in now, as you can see here, okay, then you have to produce a magnetic field.
Yes.
Then you have a nice magnetic moment here, produce a stray field, which you can see here.
That will be sensed by the GMR, or TMR.
Yes. Which is perfect, right? And because it's not cancelling like we in the previous case. And also because it's right on top of each other, right? You can get pretty much the field
for maybe low current.
Yes. So if it's X, you get a nice BX field. Okay. Now,
how much current it will be?
I would say about for what?
To produce the magnetic field.
About 20-30 milliamps.
Okay.
Yes. And for the GMR, of course, needs a current as well because we have to measure that resistance change. That is about, let's say, 1 milliamp.
Yeah.
Okay. Now again, you can Now, but remember, we also said the further away this bead is away from the GMR sensor,
Less sensitive.
right? So
Correct.
keep that in mind. So, and obviously you can also have your substrate here, okay, and then you can have your conducting coil here, and some passivation on top of it, and then you can have your GMR sensor here. Okay, so this is your GMR, this is your conducting wire, and then you have another passivation, and you can have your bead. Same thing, but you switch the GMR, right? This way, maybe you can somehow
The field seen by the bead will be slightly lower,
right? Yes,
but the change seen by the sensor, I mean, GMR may be higher
maybe higher. Correct.
because it's closer.
Yes. Okay, so this way you can get an integrated circuit. So then, what is the problem with this though? What do you think is the problem with this?
Looks good only.
Looks good. So you have your GMR, let's say. We'll
Yeah.
take a GMR. So GMR is what, 4 layers? 1, 2, 3, 4. Let's say this is your end.
Maybe it is heating.
Yes. So that good point.
Mm.
This is your pin layer.
Yeah.
This is your non-magnetic layer. This is your free layer. Okay. So this can move both ways. This is pinned. Now, you give this a current.
Yeah.
So this will produce some field. Okay. So this produces a magnetic field. Correct?
Yep.
What else? Sense current. So when you give it a current, that's fine.
By the way, what is F?
Oh, ferromagnet.
Okay.
Actually, sorry, free layer. I think pin layer.
Yes.
Pinned and free ferromagnet, something like this. Yeah. So why do we need to give this a current? Because any resistance change for us to measure. Okay. What else is there? You have your conducting wire. You remember?
Yeah.
Now, that also produces D.
Correct.
A B. Now,
Going to combine these two?
no.
No.
This is due to the excitation current.
Hmm.
Okay. Then you have a bead.
Yeah.
Which has a magnetic moment.
Yes.
That also produces B.
Yeah.
Right. So now we have 3 magnetic flux sources.
Yeah.
But we are interested in only this
change in that. Correct.
So how are we going to? And this is.
But that requires an external field.
Sorry?
This bead requires an external magnetic field.
Yes. But what we want to measure is the stray field.
Hmm.
But generally, the stray field is much smaller than this B produced by the excitation current and this B.
Hmm.
So this is probably hiding within this larger magnetic fields. So how do we extract this? Because if you think about
It's a small change on the top of the hill.
Yes, exactly. So, because this beat signal also, right? This moment, what is that proportional to? I mean, this moment, and field that it produces is proportional to this
field that you are giving.
Yes, this excitation current and this, right?
Correct.
The current, the sense current, let's say. So ideally, if you increase this, then you would get a very high stray field.
Yes.
But what is the problem with increasing the excitation and the sense count?
One thing, self-heating, also power dissipation.
Exactly. Because remember, this is a very small chip.
Yeah.
Right?
Yeah.
So there'll be a lot of on-chip dissipation.
Yes.
Which will raise the temperature of the chip.
Yeah.
And might destroy whatever it's on that chip.
Correct.
So we cannot do that. Then, so how can we then increase the SNR? What is our other option?
What is SNR? I forgot.
SNR is
signal to noise ratio. I think we discussed in some previous class.
Yes. Noise ratio. how can we improve this now? Because we cannot increase the current.
Hmm.
Then what is our other option? If you look at SNR, if you look at some of the words here, what is our other option?
Somehow the noise has to be reduced.
Yes, we have to somehow minimize the noise. So because this stray field, right, is very small, right? So it operates in the linear region of the curve, right? But it's very, very low.
Mhm.
Okay. Let's say about an ohm change or milliohm change maybe.
Okay.
Right?
Mm.
So what does this mean?
Because the change for the TMR is in maybe mega ohm range.
So
Or at least kilo ohm range. Yes.
even if it's kilo ohm, right? If you go to ohm, that's still like an order down, right?
Yes.
Right? But this also means your changing voltage is also very small.
Very, very small.
Right? Very small. So how are we going to do this?
You need some signal processing.
Yes, you need some signal processing, but in order to use some signal processing, you also have to figure out what are the different noise sources that will affect this signal. Now, we've talked about the current and all that. Fine. Those are adding, but other things, right, contributing to this noise. Before that, very quickly.
What's this very colorful slide?
Yeah, just to show you, right? I mean, these beads that we're talking about. I mean, I want to give some context to the students. You talked about the heat, right? These are very small chips, right? This is 50 micrometers. This is a whole chip here, right? And these beads are nanometer size.
Okay.
Right? So imagine you cannot heat these wires too much, right? These are micrometer tiny wires, right? So you cannot, but there's an example of how you have, let's say the previous diagram I showed, you have your TMR sensor, you have then also conducting wire, right? That produces magnetic field. Okay. And then you have, let's say, beads here that are on top of that, right? Based on the stray fields of these beads, and the TMR sensor is under, right? You'll be able to measure magnetic fields.